are two basic mechanisms for regulating blood pressure. Short-term mechanisms, which regulate vessel diameter, heart rate, and heart contractility, and long-term mechanisms, which regulate blood volume. Your goals for learning are to compare and contrast the short-term mechanisms that respond to rising blood pressure with the short-term mechanisms that respond to falling blood pressure. To understand the process of long-term regulation of low blood pressure. To describe the long-term and short-term effects of increased osmolarity on blood pressure. Here's what you need to know. The factors that affect blood pressure and the factors that affect cardiac output. To see definitions of terms, click the bold red words. Let's begin by looking at the short-term regulation of rising blood pressure. In response to rising blood pressure, arterial walls are stretched, stimulating baroreceptors in the carotid sinus, aortic arch, and other large arteries of the neck and thorax. As a result, these receptors send off a faster stream of impulses to the brain. Click on the carotid sinus or aortic arch to see these afferent nerve impulses traveling to the brain. In response to increased stimulation from the baroreceptors, the brain increases parasympathetic activity and decreases sympathetic activity. This leads to a reduction in heart rate, an increase in the diameter of the arterioles, and therefore lower blood pressure, bringing blood pressure back down to normal levels. The next two screens illustrate the reduction in heart rate and increase in arteriolar diameter. Let's look at the effect of increased parasympathetic and decreased sympathetic activity on the heart and blood pressure. With increased activity of the vagus nerve, which is part of the parasympathetic nervous system, and decreased activity of the sympathetic cardiac nerve, heart rate is reduced. This leads to lower cardiac output and therefore lower blood pressure. Click on the brain to see the efferent nerve impulses. Watch the effect on heart rate and blood pressure. Now let's look at the effect of decreased sympathetic activity on arterioles and blood pressure. Vasomotor fibers are sympathetic nerves that innervate the smooth muscle of blood vessels. With decreased activity of vasomotor fibers, the vascular smooth muscle relaxes, arteriolar diameter increases, and blood pressure is reduced. Click on the nerve to see reduced vasomotor fiber activity. Watch the effect on the diameter of the arteriole and the blood pressure. Let's recap the short-term regulation of rising blood pressure. Click on the carotid sinus or aortic arch to begin the process. In response to rising blood pressure, baroreceptors stretch, increasing impulses to the brain. This leads to increased parasympathetic activity
and decreased sympathetic activity, resulting in slowing of the heart rate and increase in the diameter of the arterioles and consequently a reduction in blood pressure.
Now let's look at the short-term regulation of falling blood pressure. When blood pressure drops suddenly, the baroreceptors are inhibited and they send fewer impulses to the brain. As a result, parasympathetic activity decreases and sympathetic activity increases, leading to an increase in blood pressure via three mechanisms. 1. Increased sympathetic impulses to the heart increase heart rate and contractility. 2. Increased impulses to the blood vessels increase vasoconstriction. And 3. Increased sympathetic impulses to the adrenal gland stimulate the release of epinephrine and norepinephrine into the bloodstream. These hormones enhance heart rate, contractility, and vasoconstriction. Together, these three mechanisms bring blood pressure back up to normal levels, as illustrated on the following screens. First, let's look at the effect of increased sympathetic activity on the heart and blood pressure. Increased sympathetic impulses to the heart and decreased vagus nerve activity lead to increased heart rate and enhanced contractility, increasing stroke volume. These changes result in higher cardiac output, which increases blood pressure. Click on the carotid sinus or aortic arch to begin the response to declining blood pressure. Watch the effect on heart rate and blood pressure.
How does greater sympathetic activity affect arteries and blood pressure? Increased vasomotor fiber activity leads to constriction of vascular smooth muscle. The smaller arteriolar diameter gives rise to increased blood pressure. Click on the nerve to see increased sympathetic activity. Watch the effect on arteriolar diameter and blood pressure.
Now let's explore the effect of increased sympathetic activity on the adrenal gland and blood pressure. Increased sympathetic impulses to the adrenal gland stimulate the release of epinephrine and norepinephrine into the bloodstream. These hormones increase heart rate, contractility of the heart, and vasoconstriction of blood vessels, thus increasing blood pressure. Because they are carried in the blood, these hormones act more slowly than nervous system controls, and their effects are more prolonged. Click on the carotid sinus or aortic arch to begin the response to falling blood pressure. Watch the effect on the adrenal gland, the heart, and blood pressure. Here's a recap of short-term regulation of falling blood pressure. Click on the carotid sinus or aortic arch to begin the process. As blood pressure falls, baroreceptors are inhibited, resulting in decreased impulses to the brain. We will now explore the long-term regulation of low blood pressure. Long-term regulation is primarily accomplished by altering blood volume. The loss of blood through hemorrhage, accident, or donating a pint of blood will lower blood pressure and trigger processes to restore blood volume and therefore blood pressure back to normal. Long-term regulatory processes promote the conservation of body fluids via renal mechanisms and stimulate intake of water to normalize blood volume and blood pressure. Here, we will simulate the loss of blood and demonstrate the chain of events which will restore blood volume and normal blood pressure. Click on the blood collection bag.
Granular cells in the kidney monitor alterations in blood pressure. If blood pressure falls and remains low, these specialized cells release the enzyme renin into the bloodstream. Click on a kidney to start the process.
The renin-angiotensin mechanism consists of a series of steps aimed at increasing blood volume and blood pressure. Step 1 is catalyzing the formation of angiotensin 1. As renin travels through the bloodstream, it binds to an inactive plasma protein, angiotensinogen, activating it into angiotensin 1. Click on the renin molecule. Step 2 involves converting angiotensin 1 to angiotensin 2. As angiotensin 1 passes through the lung capillaries, an enzyme in the lungs converts angiotensin 1 to angiotensin 2. Click in the box below. In the third step, angiotensin 2 stimulates aldosterone release. Angiotensin 2 continues through the bloodstream until it reaches the adrenal gland. Click in the white box to see a close-up view of the adrenal gland. Here it stimulates the cells of the adrenal cortex to release the hormone aldosterone.
A secondary effect is that the angiotensin 2 is a vasoconstrictor and therefore raises blood pressure by constricting the body's arterioles.
The aldosterone mechanism is an important component of long-term blood pressure regulation. The target organ for aldosterone is the kidney. Here, aldosterone promotes increased reabsorption of sodium from the kidney tubules. Click in the black box to see a close-up view of the kidney.
The distal convoluted tubule winds through the kidney and eventually empties its contents into a collecting duct. The paratubular capillaries absorb solutes and water from the tubules and collecting ducts as these substances are reclaimed from the filtrate. Aldosterone stimulates the cells of the distal convoluted tubule and collecting duct to increase the active transport of sodium ions out of the tubule into the interstitial fluid. Click in the peritubular capillary to demonstrate the effect of aldosterone.
As sodium moves into the bloodstream, water follows. The reabsorbed water increases the blood volume and therefore blood pressure.
Click in the collecting duct to show the movement of water.
Dehydration due to sweating, diarrhea, or excessive urine flow will cause an increase in osmolarity and a decrease in blood volume and blood pressure. As increased osmolarity is detected, there is both a short-term effect and a long-term effect. For the long-term effect, the hypothalamus sends a signal to the posterior pituitary to release antidiuretic hormone, abbreviated ADH. ADH increases the reabsorption of water in the kidney.
ADH promotes the reabsorption of water from the kidney by stimulating an increase in the number of water channels in the collecting tubules.
These channels aid in the movement of water back into the capillaries, decreasing the osmolarity of the blood and increasing the blood volume and therefore blood pressure. A short-term effect of increased osmolarity is the excitation of the thirst center in the hypothalamus. The thirst center stimulates the individual to drink more water and thus rehydrate the blood and extracellular fluid, restoring blood volume and therefore blood pressure. Click on the water bottle.
There are many other chemicals which influence blood flow and blood pressure. Most of them act by altering arteriolar diameter. Here's a summary of what we've covered. In the short term, rising blood pressure causes increased parasympathetic and decreased sympathetic activity, which leads to reduced heart rate and contractility, vasodilation, and lower blood pressure. Falling blood pressure causes increased sympathetic and decreased parasympathetic activity, which leads to increased heart rate and contractility, vasoconstriction, and higher blood pressure.
Long-term blood pressure regulation involves renal regulation of blood volume via the renin-angiotensin mechanism and aldosterone mechanism. Increased blood osmolarity stimulates release of ADH, which promotes reabsorption of water and excites the thirst center, resulting in increased blood volume and blood pressure. To test your knowledge, click the quiz button to go to the self-quiz. To access cross-references for this topic in your Benjamin Cummings textbook, click here. To test your knowledge, click the quiz button to go to the self-quiz.